Well, hello everybody. As we gather for this meeting from different places all around Australia, talking to people all across the globe, I'd first like to acknowledge the traditional custodians of the land on which we meet. I'm joining you today from Turrbal and Yagara land in Queensland. I pay my respects to elders past and present, and to any Aboriginal and Torres Strait Islander people who join us online today. As we share and discuss our knowledge and our practices, we acknowledge the deep knowledge forever embedded in custodianship of this country. Now, I'd just like to address the housekeeping for this wonderful webinar. This is the second webinar in a series of webinars sharing successful scientists and technologists who have translated research into practical and commercial products. The series is being put together by ATSI, the Industry and Innovation Forum of ATSI, the Academy of Technology and Engineering, and it's a learned academy helping Australians understand and use technology to solve complex problems. We bring together Australia's leading thinkers in applied science, technology and engineering. The theme of this webinar is Space, a webinar which aims to discuss multifaceted challenges and opportunities underpinning research, innovation and commercialisation of the space sector. The format of the session will be in 4 short talks, one after another, and attendees are encouraged to submit their questions anytime via the Q&A functions down at the bottom of the screen, but they will be addressed together after the talks in a Q&A session. Attendees are welcome to use the chat function to engage with each other through the session, but make sure questions only come through the Q&A section. Attendees are also very welcome to tweet along using the hashtag @ATSIInnovationNation. Now I'd like to introduce our host, Professor Saeed Nadavanti of Deakin University, who was named winner of Australian Defence Industry Awards Innovator of the Year for 2021, winner of the Essington Lewis Awards, recognising Excellence in Defence Projects 2021, Professional Engineer of the Year for Victoria, winner 2021, and finally, Australian Space Researcher of the Year at the 2021 Connect Australia Space Awards, which recognise the leading individuals and businesses driving the development of Australia's space economy. Professor Nadavanti, welcome.
Thank you very much. Thank you for your very kind words. Now, let me begin what I see as being an exciting initiative. Moon to Mars initiative, Trailblazer Stage 1 announcement by Department of Industry, Science, Energy and Resources, Australian government. This $150 million grant provides an opportunity to leverage and diversify Australia's world-leading remote operations skills and experience by developing new foundation services capabilities, encouraging investment and opportunities in the Australian space sector. We believe that it supports Australian businesses and researchers to join NASA's inspirational endeavor to go forward to the moon and then go to the Mars. Working in isolation no longer provides the immense benefits that results from international collaboration and is believed to be a key to accelerating the realization of the Moon to Mars initiative of Australia. Hence, it is critical to understand policies, strategies, efforts of other countries in space research and innovation. To this end, I would like to introduce our special guest from DLR, the National Space Center of Germany, which has a wide range of R&D projects in collaboration with national and international partnerships. We are fortunate to have to hear from Dr. Anger Pagels. Dr. Pagels was appointed divisional board member for space in October 2021. She's responsible for the research and development program of DLR's 2022 Space Research Institute. And obviously she's responsible for 22 Space Research Institutes. From 2016 to 2021, she was head of the Space Science Department at the German Space Agency. In this position, she was responsible for the agency's research program and space program missions in the areas of solar system research and astronomy, astrophysics. Previously, she worked as a scientist in the Satellites Communications Department and was the responsible project manager for the German part of European Data Relay Satellite System. Dr. Pagels has been a member of the Space Agency staff at DLR since 2009. She received her diploma in physics and astronomy from the University of Bonn, followed by a PhD in astronomy in 2006 at Max Planck Institute for Radio Astronomy, Bonn. Her research focused on millimeter VLBI observation of supermassive black holes. From 2005 to 2009, she was a research associate at the MOD Related Science Institute for High Frequency and Radar Physics. She was responsible for the planning and execution of NATO campaigns involving radar. I was told that Dr. Pagels is currently traveling, and during transit, she may not be able to join us live, but we have a pre-recorded video from her. I would like to draw your attention to this video.
Good morning, and thank you very much for the invitation. My name is Anke Pagels-Kerb, and I am the Divisional Board Member for Space at the German Aerospace Center. Today, I have the pleasure to talk about some of the projects of our research institutes on solar system missions. First of all, I would like to talk about Hayabusa, a trilateral sample return mission together with JAXA, CNES, and DLR to the asteroid Ryugu. Launching at 2014, we arrived at the asteroid in 2018 and were back on Earth in December 2020. On the lower right side, you can see the parachutes in white with a capsule on the right side next to it. On picture on the left side, you can see the mascot lander, which was built by DLR and CNES, and in the middle, the small capsule with the asteroids probes in it. The second is the ESA mission Bepi Colombo, a mission to Mercury named after an Italian astronomer, Giuseppe Colombo. Bepi is a combined spacecraft built by ESA and JAXA. They will be separated if they arrived at Mercury in 2025 in a magnetospheric orbiter and a planetary orbiter. Together with institutes all over Europe, we built a laser altimeter named BELA, what is an acronym for Bepi Laser Altimeter, as part of the payload. And if you build a laser altimeter once, you can also do this twice, so we will fly an altimeter on the ESA mission to Jupiter's icy moons. On the left side, you can see the altimeter in the lab, and in the middle, integrated on the JUICE platform. GALA, which stands for Ganymede Laser Altimeter, is the one with the red protective cap on the lower side of the satellite. JUICE will be launched with the last Ariane 5 at the beginning of next year and will arrive in the Jupiter systems in 2030. These missions are back on Earth or in orbit or on the way to the launch pad, but what are the plans for the next years? Last year, NASA and ESA decided about the mission on the end of the 20s, and NASA, as well as ESA, choose a mission to Venus. not landing systems because of the high pressure and temperatures on Venus' atmosphere, but both of them planned satellites measuring the atmospheric conditions of Venus and the surface with radar systems. The contribution from DLR will be infrared spectrometers, but also algorithms for the synthetic aperture radar systems coming out of our Earth Observation Center. Crossover science, but to be frank, the Earth is also just a planet. In the middle of the 20s, we will have a mascot-like mission also from the partners CNES, JAXA and DLR. In 2024, we will launch MMX, which is a sample return mission to one of the Martian moons. The last mission I will talk about is the mission without destination. Together with Ariel, an ESA exoplanet mission, we will launch 3 spacecrafts to the Lagrange point 2 in the Sun-Earth system. Then the satellites have to wait and wait and wait until an undiscovered comet makes a flyby. Then the satellites will cross the flight path and follow the comet as close as possible. For the future, several calls for ideas were published. The researchers would like, of course, to go back to the Moon, but also to discover the fountains of Enceladus, go to the icy planets Uranus and Neptune, and bringing back a sample of Saturn's atmosphere. So you can see we will have lots of work to do, building spectrometer, cameras, landing systems, altimeters, and much more other payloads. Thank you for listening my talk, and stay healthy.
Thank you very much. Very interesting and insightful indeed. We know that the mission of the International Space Station is to enable long-term exploration of space and provide benefit to people on Earth. To send people into space require much training, and the notion on limitations on human biophysiological endurance capabilities in space and aerospace environments. Our next speaker has much expertise in this field. Dr. Bhupi Singh specializes in aerospace medicine and is a qualified fighter pilot. He has 35 years of experience in the field of aerospace medicine, including human engineering and acceleration physiology. He has worked with the Indian Air Force, Air India, and the RAAF. Currently, he is an honorary professor at Deakin University. Over to you, Professor Singh.
Thank you, Syed. Thanks for the wonderful talk we heard from the German side and their future missions. My main interest, especially in relation to this particular mission, is the human space flight. Any country that talks about or considers space exploration have to eventually think of a manned mission. It may be a manned mission to a nearby planet, or maybe further off into the galaxy. But the bigger question on that is, the manned mission has been going on in the world for the last 60 years, from 1961 onwards. And almost 600 people have visited the space from 42 countries, although only 4 major nations have developed a full-fledged capability and the technology to put humans into space. But a lot of other countries have piggy-ridden on other countries. So the first question that arises for us, which we have to decide on whoever is pushing this mission, they have to decide whether at some stage in the future, we are considering putting humans into space, whether independently, developing full technology and full processes, or piggyback riding on some other nation. That's a huge, huge difference. Because the challenges of space flight, challenges of human space flight are plenty, but most of them have been sorted out or solved, I would say, by technological innovations. Problems like vacuum of space, where what kind of pressures do we use inside a spacecraft or human capsule? The Russians have been from beginning using a full pressure 760 millimeter, 14.7 psi pressure inside the capsule. That produces a huge uh, pressure difference between inside and outside. The Americans on the other side, in the space station and in the space shuttles, have been using half the atmosphere, 380 millimeters of mercury, with 40% oxygen. So oxygen pressure, partial pressure comes back to the Earth-like level, but the total pressure is less. That reduces the pressure differential between inside and outside. So this is a major difference which countries have to decide which system to follow. When the Soyuz and American spacecraft rendezvous took place, somebody had to change their system so that both are compatible. Obviously, the American systems were unable to withstand high pressures of 760 millimeters. So the pressure on the Russian side was dropped to half. So those are just examples of challenges. The second is the high acceleration during launch and during re-entry. A lot of simulation is required. We need simulators to produce that on the ground. Then during the space sojourn, there is weightlessness, which itself is a big problem. In the space, having no weight is actually an advantage. You can do things, you can float around, there's no weight. But because you don't need muscles and bones in space, not to that extent. So there is a lot of demineralization of bones, weakening of muscles. So when you return back to Earth, that's a big problem. And you cannot cope with even 1G. So one has to constantly produce some kind of gravitational force while experiencing space weightlessness, either in the spacecraft or on another planet. The second big challenge is the radiation. Whenever you expose on the surface of the Earth, by Earth's atmosphere. Once we leave the Earth's atmosphere, you're exposed to cosmic radiation, solar flares, things like that. And they can be pretty harmful to the human body and human systems. So one has to find methods to avoid that, to minimize the effect, and to time it accordingly. So these are the second challenge about that. But the biggest challenge of long duration space flights is the isolation. If you put 2 people or 4 people or 3 people together in one room and leave them alone for 1 year, you can imagine the interaction that goes on between them. So that's where the selection of a crew plays a big part. To overcome these challenges, since we already have the technology, but a lot of astronaut training is required, and that training basically requires simulators. And a lot of countries have built those simulators. They cost huge amount of money and a lot of experience to run them over a period of time, like centrifuges, water immersion tanks, parabolic flight aircraft, hyperbaric chambers, isolation chambers, things like that. So before we go into details of these, not in this particular talk, but at some time in the future, we got to take considerations. And the last thing I would like to say is, which is not really medical related, is that what we are doing for the space flight today is fundamentally rocket-based. And rocket-based technology is hugely inefficient. Any rocket going into space can carry only 5% of its weight as payload. 95% is fuel and other things. Compare this to an aircraft, which is an air-breathing engine, which can take 66 to 70% of its weight as payload. A 747, which weighs only 150 tons, can carry 300 tons of payload. So total weight of 450 tons. That's a much bigger, better way of doing things. The newer space initiatives have used an aircraft to raise the human beings to a particular altitude, say 80,000, 70,000 feet, overcome most of the distance, gravity-wise, and then launch a rocket from that space, that into space. That would reduce the weight of the rocket. And other technologies are on work. If we have to go anywhere beyond our near planets like Mars, or we need to come up, the engineers need to come up with a better technology, a better engine, a better fuel, so that we can carry humans into space at a much lower cost than is currently possible. Thank you very much.
Thank you very much, Professor Singh. Next, let's focus on the need to have advanced robotic and autonomous systems capabilities as one of the main ingredients for Moon to Mars initiative. For this webinar, we have Dr. Edward Tunstall as a leader in robotics and autonomy. Dr. Tunstall received BS and ME degrees in mechanical engineering from Howard University, Washington, DC, and the PhD in electrical engineering from the University of New Mexico, US in 1996. He served as a leader in robotics and autonomy with NASA's Jet Propulsion Laboratory for nearly 2 decades. Johns Hopkins Applied Physics Laboratory for a decade, and Raytheon Technology Research Center for several years. He's currently CTO with Motive Space System, Inc. His interests span research through deployment of robotic and autonomous systems and documented in over 170 publications in those areas, and as manifested in substantial contribution to robotic system for space and planetary exploration. He's an IEEE fellow and served as 2018-2019 president of the IEEE Systems Man and Cybernetic Society. Without further ado, I would like to ask Dr. Tunstall to share his expertise on robotics and autonomous systems.
Thank you very much, Dr. Nadavanti. I will share my screen as a backdrop to the things I intend to talk about. I'm doing that now. Okay, do you see my screen?
Yes, we see you.
I'll take it that you do. Okay, very well. Well, thanks for this opportunity, number one, to have an opportunity to share with you some of my experience and feelings about the challenges and so forth associated with space robotics. This is the field that I've been concentrated on for some decades, as just mentioned, and I can speak to various aspects of what's been going on in this area. This collage of images is really a mixture of research projects that I've been involved in or affiliated with, as well as some actual space flight projects, some of which are in the past, some are ongoing, and some are in the near future. But I want to just sort of give these visuals to assist what I'm talking about, just so that everyone has a sense for what's involved and what types of systems I'm referring to. This is a complement, if you will, to what Professor Singh talked about regarding human space flight. So I'm going to talk primarily about non-human space flight, in particular, robotic spacecraft and systems. And generally, when we're exploring the various parts of the solar system, we tend to approach those things in a certain way, typically with some form of reconnaissance or set of reconnaissance missions where we're looking to fly a spacecraft by a planetary body to get more and more information such that we learn more about the environment, understand whether or not it's possible to potentially land at various locations, and that sort of thing. And following that, we tend to send additional missions that may actually land on the surface, and certainly missions that may actually land and then rove on the surface. So all of these are multi-year campaigns to understand more about the target destinations that we intend to try and explore. Certainly closer to Earth, we're looking more intently these days at on-orbit servicing or in-space inspection types of systems that are robotic. And these start to lean more in the direction of commercial applications. So there's exploration and utility robots that apply very, very much so to the types of exploration missions we do in outer space. And then there are on-orbit robots. Think of satellites, for example, with robotic arms, such as in the upper left of the set of images here that you see. These missions in particular are becoming more and more popular and in demand these days because of the commercial sector component. The idea being that we could actually extend the lifetime of certain satellites that are currently in orbit by allowing a robotic system to go up and service them and extend their life in various ways, whether it's via repair or whether it's via adding additional fuel to that system or what have you. Certainly for much larger systems like the International Space Station as one example, there's robotic solutions for flying different types of robotic craft outside of such a space station to inspect and ensure that there aren't damaged parts of that, that space station. That, for example, robots or even astronauts would have to be called upon to do repairs and such. There's lots of different applications. But the main thing that I want to really portray here is that in order to get deeply into providing systems for these various applications, one of the biggest things to worry about is the space environment that the system is intended to go to. A lot of these technologies, especially in the area of robotics, are very prevalent, in fact, on Earth, as you may know, and in factories, as well as in field robotics applications. And I'm sure many of us have seen various videos of different types and varieties of robots doing very interesting things. But they, by and large, they are not in a condition, hardware-wise mostly, to actually survive the planetary surface locations that we intend to explore or the environments in space. And so while the technology in terms of robotics may exist today for various types of applications, they're not directly transferable to these missions unless we solve and address the hardware problems. And this has to do with challenges related to the radiation effects on electronics, the thermal environments, such that our current laptop computers, for example, will not survive many of the environments because of radiation and thermal effects. And indeed, in terms of mechanical hardware as well, motors, joints that move. We try to minimize the number of different things that move on any type of space hardware because of some of these issues. But there are many challenges to address depending on the system that you're involved with, as well as the target environment. And that becomes a large part of the technology development, the technology advancement, and indeed the enabling technology that allows various missions to occur. That aside, of course, in many of these cases, such as Mars missions, for example, you have systems that are operating very far away from where we are in terms of operating the mission overall. And so they must be very robust in various ways. If they have any degree of autonomous function, that's a key area where they have to be very good at what they do and very resistant to faults that may occur. But faults do inevitably occur. And so there must be built into the system a means for us very far away from those systems to be able to intervene in various ways to recover from faults and to do whatever is necessary to allow the mission to move forward. So there's lots of different challenges, and I couldn't really delineate them in a very easy fashion without talking specifically about certain missions. What you're seeing here on these images are mostly planetary surface types of systems, again, some of which have been delivered to planetary surfaces, but as well research activities. And I may talk about some of that later because there's definitely a path from research activities into these spaceflight missions. But there's lots to be done between the laboratory or the field application or experiment and the actual deployment on a real mission. Many people involved, many different applications and technologies involved. And it's definitely a team sport, but one in which there's lots to learn for anyone who's looking to get involved in a major way from not being involved prior. So it's a tough field to get into, but lots of technologies that are going on and being developed and are available, in fact, within universities in Australia, within other research organizations within Australia, are indeed applicable. They just need to be conditioned, if you will, and perhaps matured or improved in certain ways to survive the challenges of the space environment and the fact that none of us are nearby to recover them from the various faults and failures. So I'll go ahead and stop there. Just wanted to leave this as context for the rest of the discussion. Thank you very much. I'll stop sharing my screen now.
Thank you so much, Dr. Tunstall. Amazing. Next, I would like to stress the importance to have a vibrant local environment to promote research and innovation pertaining to space science and technologies in Australia. We are glad to have Professor Andy Corone, CEO and Managing Director of the Smartside CRC, with us in this forum. Smartside CRC is a consortium of universities and research organizations partner with industry to develop know-how and technologies for the space sector that will spawn new businesses, create export economic value, and generate new high-tech jobs for all Australians. Professor Corone is a professor of information systems and previously held the positions of Dean, Industry and Enterprise, and head of the School of Information Technology and Mathematical Sciences at the University of South Australia. I would like to invite Professor Corone to share the work of the Smartside CRC and how Smartside CRC contribute towards advancing space capabilities in Australia.
Thank you so much. Thank you for highlighting this. Thank you very much. It is really amazing. I'm certainly have missed quite a bit of the great work that has been done due to another meeting, but thank you for the opportunity to speak to you very briefly about the work of Smartside and how it actually works to build capability here in Australia. Australia, as you probably have been told, has some specific world-class capability in a number of areas related to space, but we have been very late to the party. But with great leadership from our space agency and our governments, we are now really working very, very hard to address this so that we can become a space-capable nation. We in the Smartside CRC have brought together a collaboration, a large consortium, the largest in the history of Australia in terms of space, of global companies, SMEs, as well as smaller startup ecosystem, working hand in hand with our government research labs, with our civilian research labs, and of course, our academia, our fine universities here in Australia. We have won over $250 million in R&D over the next 4 years now. And we will apply these in a number of areas, primarily in telecommunications and IoT, satellite communications and IoT, in the areas of artificial intelligence, as well as the next generation of Earth observation sensors, as well as the analytics that goes with it, to produce next generation of space information products. We have approached it in capability demonstrators, what we call a mission-oriented R&D, and we have 3 of those. One is around monitoring the quantity, the flow, and the quality of water across Australia, a very, very important area for us. The second one is around preventing, preparing, and responding to disasters, around disaster management, and particularly for us, bushfires or wildfires for the non-Australians. We are very keen to actually ensure that we use space technologies to really reduce the loss of, eliminate it if we can, the loss of life and certainly the loss of property due to these climate change induced problems, extreme weather events. And finally, of course, our third capability demonstrator and mission is our Indo-Pacific connector, which looks to actually provide tactical and ad hoc type of communications to our Defense Department. And we have some projects helping primarily the work of defense and national security. How we build capability, we have only been operating for the last 3 years. We've brought together a startup cluster. We have a doctoral training program, over 70 PhD scholarships, full scholarships for students. We've got a distributed model. We are establishing centers, helping our universities to establish centers, nodes, and space hubs. We have a program where we co-invest with universities around having professorial chairs. And in fact, I'm on an interview panel very shortly about one of those. We will have 9 of those. We've completed already 4. We have an international visiting researcher scheme. Unfortunately, the borders have been closed up to now, but we are very keen. And yesterday, in fact, I had a meeting with the MD of Airbus Defence in the UK, and we've agreed to have some international internships of students from Australia moving into other areas, not necessarily only the UK, but through international internships. I was given 5 minutes, so I'm now over those 5 minutes. Thank you very much for giving me the opportunity to, in a fast forward, talk to you about Smartside and our contribution to the ecosystem.
Many thanks, Professor Corone. Really appreciate that. This is a great segue for our panel discussion. Now, I would like the panel members to comment on the potential pathway for translating innovative space-related technologies developed by universities and research institutions into commercial products. Anyone from?
That is a good question. I can take that or start it out at least. So this is effectively the path that I've lived on, if you will, throughout my career. Started out really doing focused research all the way from very low technology readiness levels to higher levels that make technology actually ready in a technological sense for real space missions. And I still operate on both sides of that fence effectively. And so I've seen this path operate and the various ways in which it can actually be successful, and certainly the many ways in which it may not be as successful. Primarily, those who are doing research that's related to space types of applications, unless they are already well embedded into that arena in terms of being close to space missions or what have you, or the hardware that will enable those missions, there's a learning curve, at least, to get to that point. But there are many people who can be collaborated with, whether they're in other space agencies in other nations or within country, that can help along that path. But as you might imagine, there are many researchers doing very interesting research, but only a small amount of their results actually impact space missions. There's many different reasons for that, some of which are really associated with the risk-averse nature of space flight missions. And what I mean by that is that certain technologies that work well in laboratories or even in the field, in certain settings here on Earth, for various reasons may not be ready for or may not be robust in certain space environments. And so there's typically a technology maturation path that is often many, not many in all cases, but certainly a number of years, where it takes time to, number one, understand what it is about these space environments or the systems that are being targeted for development that would enable that technology to actually fit within such a mission. And then what are the necessary challenges that need to be overcome in terms of development in order to mature those technologies to the point where they can be seriously considered as viable solutions. Myself and many of the colleagues that I've worked with over the years, we constantly live on this particular path. Some of us are doing research today, as we have been doing some decades ago, and some like myself have had the opportunity to also see those things in use on real spaceflight missions. For myself in particular, when I have that experience, that latter experience, to actually have something that I've been involved in developing or maturing, used on a space mission, that typically informs me of the real problems that need to be solved in advancing the technology even further. And so I go back to the laboratory and do more research, but in a much more focused way. So it's really, I think the pathway to, the potential is high for getting relevant technologies onto certain space missions. The pathway is long in some cases, depending on the ambition of the mission, the severity of the space environment that it is going to, and the current state of that technology, relatively speaking. So it's definitely a possibility for many types of technologies, new ideas, and so forth, to make it on the space missions. But the risk-averse nature certainly calls for not only selling, if you will, the technology's capabilities such that people believe that it can actually be effective, but also there's a sort of chicken and egg type of a situation when it comes to whether or not certain technologies or the bulk of those technologies has been flown on space missions in the past. In other words, is it proven, or is some major aspect of it that could lead to a significant failure proven, such as electronics or something like that, or certain algorithms and so forth. So there's a lot of different work going back and forth to try and ensure that everything matches up in terms of technology readiness, and then has the actual opportunity to fly on certain space missions. And so it's definitely a path that exists. It's a little bit rugged to navigate that path, but the key is understanding the environments, understanding the technology, and maturing the technology to the point where it is a viable solution in the targeted space environments.
Yeah.
Thank you. Any other panel members would like to comment?
I can just briefly echo the great answer that was given about this. From my perspective, it is, first of all, it is hard. It's not easy. It's easier for us to say, but it's very hard. The way that I see it and the way that we try to do it with Smartside is that, you know, as we know, really research turns dollars into ideas, if you like, or invention ideas, and innovation turns ideas into dollars, the commercialization path. But for that to occur, as you've just heard, we need three distinct elements in my mind. We need to have, first of all, the ideas, the innovation, something that's new, but we also need the implementation, that testing, that heritage that it needs to actually have before it becomes something that people may use. But unless it's actually used, unless there is improvement and use, then innovation is very difficult. What we do with Smartside is we bring the researchers, the industry, the technology makers, but also the end users, you know, the farmers, the emergency management, the miners, the people that will actually use the information products that will come out of the satellites, whether it's comms or EO and so on. We bring them together from the beginning so that when we have ideas, when we have an invention, we don't here in Australia say, okay, now how do we commercialize it? And typically what happens, it actually flies overseas. Because the industry is part of that team, they put their hand up to commercialize it.
Fantastic. If I may, are there any other responses here, or shall we? Okay, I have another one that would be very interesting to get the panelists' view on partnership between industry practitioners and academic researchers in building space capabilities for Australia. Maybe Andy wants to comment on that, especially yourself and Smartside CRC have done such a superb job.
Oh, thank you so much. Thank you. We still need to improve because, again, the partnerships are not easy. It's easy for us to say there has been, at least in Australia anyway, there's been a little bit of a cultural chasm. Academics are incentivized by things that are probably not as in fact, in the old times, academics found it almost, what's the word? Not desirable for them to actually have their work have impact. They just wanted to write papers. They wanted the papers to be cited, and as they still do, but the impact was not really measured. They didn't get promoted on the impact. They got promoted on the quality of the research. So there is a cultural difference in what industry wants, which is quick solutions now, and something that is useful, to what academics are working on. And they need to be given that freedom and creativity, because that's where the great ideas come from. But we need to be building the bridges, to be able to build the bridges so that there is an understanding between industry and academia, and there is an incentive and a satisfaction for the researchers to be able to say, wow, you know, my software is on the rover that's going to Mars, or my technology is used by miners, to have that kind of, if you like, incentive for academics to do that. But partnerships are hard. We've managed here in Australia to actually bring a lot of partners together, and I think the attitude is changing quite a lot now. The universities are very, very open, very ready, and in fact, they're getting quite a lot of professional support in order for them to make it easy to connect to industry and partner with industry. So I think the future is very bright for Australian university industry partnerships.
Thank you. And maybe let me open it up a little bit in terms of international, the importance of international collaboration in establishing a global space industry. Would anyone would like to comment on that?
I can say a few words in that direction. So in my experience, you know, some 30 years or so, working primarily within the confines of NASA missions, I found that international cooperations and collaborations and partnerships are very important. Primarily, as was mentioned earlier, a lot of what we do in the space sector is extremely expensive. Even before you get to the actual spacecraft and the missions, even getting there to that point is expensive in terms of developing systems and so on. And it's very rare, it seems, that any individual country or its space agency, if you will have all of the available funds to fund everything that they want to do on a particular mission. And so it's very, very common to have international cooperation and collaboration so that you can actually do anything of substantial importance that the various nations involved are interested in doing. So I would say that in my experience, this definitely has been a modus operandi, if you will, in terms of how we actually achieve many of the things that we do on various missions. And certainly something like the International Space Station is a prime example, something that would not exist were it not for the collaborations and partnerships of many different countries involved.
Thank you. I guess I have one more question, that what do you see as the biggest challenge for Australia to enter the space race? You know, it's, if there is such a thing, what do you see as being the biggest challenge? Obviously, finance is important, because already the other countries, they have poured billions of dollars, and Australia is starting this journey.
Just a personal view, I'd like to allow my colleagues to comment first.
Yes, I'll give that a shot. I don't know everything that I probably should know about what's going on in Australia in this area, and so my response here is less informed than I would otherwise like it to be. But I would say that certainly, you know, that learning curve that I referred to is a big deal. And I think that you can navigate that learning curve to get to a point where the severity of various environments and what the implications are for the technology are well understood by collaborating with those countries that have actually done various things. You learn a whole lot from those collaborations, and certainly it helps lead to your initial missions that you lead or have a significant part of yourselves. And so I think that there's definitely the learning curve, you know, beyond the funds, assuming that you have the funds available to do various things. There's lots to learn to avoid early failures in your systems. And even for those countries that have been doing this for a while, as you've noted from reports that have come out from various missions in the past, failures still happen. And so even with lots of knowledge, sufficient funds, really smart people, and so on and so forth, sometimes the space environments are not very forgiving and often very more challenging than we anticipate them to be. And so certainly as far as up as you can get on the learning curve by collaborating with others who have been involved in this area, the better off you'll be.
Thank you. Yes, and
I can make a quick comment, Said, if you allow me.
Absolutely, please.
Yeah, thank you very much. I think that, thank you very much. I think what Dr. Tunstall said is very, very important. And indeed, what he said, even in the answer of the previous question, is extremely important as well. From my perspective, I think there are quite a number of challenges for Australia. First of all, as they say in ice hockey, don't follow the puck, but you try to anticipate the trajectory of where the puck will go and try for that. Australia is not on a plain level field. We are coming from behind. So we need to learn fast, but learn fast, not in all areas. We can't do everything. Even large countries cannot do everything. So we need to focus on things that will provide value, in my view. And to do that, we need to take a model of master apprentice, where we need to work with larger companies and larger organizations. So that's the issue of collaboration with NASA, with ESA, with all the global players that know this game far better than we do. Collaborate with them and be the apprentice in most areas so that we can learn and transfer that knowledge here in Australia. And then finally, I think we need to also scale. Australia needs to scale. We are just a small country, and therefore, how can we scale our companies, the emerging great startups and SMEs that can actually add value? How can we scale them? And in my view, I think that our government has been fantastic. The government has been, don't worry about money. There's plenty of money in terms of investing. So government as an investor, they are doing a brilliant job. The next step is for them to be government as a customer. We in Australia will need customers so that we can build our supply chain, we can build our confidence so that international companies will look at us and say, yeah, actually, we could buy from Australia on space assets, particular areas, of course, not everything. That's my personal view.
Fantastic. Thank you very much. Amazing. Thank you. So unfortunately, the time is very short and we need to bring this session to an end by drawing some concluding remarks. The changing nature of the global space industry bring new opportunities for Australian businesses. The Australian Space Agency stated this rapid transformation of industry and the space sector is one of the many reasons why Australia can harness greater share of the global space economy. There are a growing number of business opportunities, and Australian businesses have a range of capabilities that can diversify into the space sector. This means that unlike traditional systems and structure for involvement in space, government's role can be one of a partner and facilitator. Therefore, in line with SA's statement, it is timely and aptly to foster a multi-tripartite international network encompassing universities, research institutions, industries, being startups, SME, multinational cooperation, along with support of governments to leverage the opportunities in this space sector. This webinar has brought together national and international subject matter experts from various domains to share expertise and experience in advancing Australian space capabilities. It is envisaged that the continuous effort of ATSI set the foundation for all stakeholders to work together in building a sustainable and inclusive global space economy. Finally, special thanks to Dr. Anka Pagels, Professor Bhupi Singh, Dr. Edward Tunstall, and Professor Andy Corone for their superb contributions today. And thank you very much for your participation. Thank you.
Thank you for the opportunity.